Most people think of electricity and magnetism as completely different, but in reality they have a dual nature. You may already know that an electric current can create a magnetic field. This is how powerful electromagnets work. But it goes the other way too. A magnetic field can actually create an electric current. This is a coil of copper wire. It has no battery or power source and zero current. But when a magnet is waved overhead, there's a spike. Let's look at what happened a little slower. When the magnet moves in from the left, there's a brief current. When the magnet stops moving, there's no current. And when the magnet moves away, there's a current in the other direction. What's going on? To understand what's happening, we need to understand how magnets interact with the particles in a wire. Every magnet, whether it's a permanent magnet or an electromagnet, creates a magnetic field that exerts force on moving charged particles. This force is proportional to the charge and the speed of the particle, so a fast, strongly charged particle will experience a large force, while a still or neutral particle won't experience any at all. The direction of magnetic force can be determined by the right-hand rule. If you point your thumb in the direction of the particle's motion, and your pointer finger in the direction of the magnetic field, your middle finger points in the direction of the force. Now let's go back to the original situation. An electric current can be visualized as a series of positive charges flowing through the wire, so let's look at a positive charge. Since there's no current initially, it's not moving. But the magnet is moving. It's moving right relative to the charge, which is the same as the charge moving left relative to the magnet. And if we have a moving, charged particle, you guessed it, magnetic force. The right-hand rule tells us that the force is directed downwards. Since every other charge in the field also experiences a downward force, they'll start to move. And the series of positive charges moving through a wire, that's just an electric current. This is where the first current we measured came from. And we can explain our other observations too. When the magnet stops moving, there's no more magnetic force, and therefore no more current. And when the magnet moves away, it's still exerting a downward force, but this time on the other side of the coil, so the current flows the other way. This current is called the induced current, and this phenomenon is called magnetic induction. But what determines the strength of the induced current? To answer that, we need to understand magnetic flux. Magnetic flux can be roughly understood as the total magnetic field that passes through a given surface, and it's proportional to the number of magnetic field lines that pass through that surface. In our example, the surface is the loop, and when the magnet moves in, there are more and more field lines inside the loop, so the flux is increasing. When the magnet moves away, the flux decreases. Looking at how the magnetic flux changes allows us to make our initial observation, that the movement of the magnetic field caused the current, more rigorous. In fact, Faraday's law states that the strength of the current is proportional to the change in magnetic flux over time. The current we initially measured was tiny, on the order of a few microamps, or about 100 millionth of your household current. But Faraday's law tells us how we can generate larger currents, by creating a greater change in magnetic flux over a shorter period of time. In fact, this is the principle by which modern generators work. A generator works by spinning a loop of wire very fast inside a strong magnetic field. Even though the magnets aren't moving, the number of field lines that pass through the loop changes as it spins, which creates a large change in flux very quickly and allows the generator to generate the large currents that are needed to power our homes. Not only is magnetic induction a powerful demonstration of the duality of electricity and magnetism, it's also necessary to power our lives.